In this video, I'm going to provide a broad overview of what this course is going to cover and what we will learn in a general way. We're not going to get into particulars, but general, what are the kinds of topics that we will be covering in this course. Okay, suppose that we start with a situation where we have a business problem. It could be in any of the functions within a business. It could be a production and operations management problem, like how much inventory we need to hold in order to make sure that the production line is not interrupted. Or it could be a service operation where we need to determine how many tellers that we should have in a bank so that customers do not have to wait too long. Or it could be a marketing situation where we want to decide how to allocate our advertising budget such that we meet certain criteria in terms of market reach or the reach of different customer segments. Or it could be finance where we want to allocate asset allocation problem, or it could be risk minimization problem, or forecasting stock prices and home prices and things like that. So it could be from any of the business functions that when a problem arises, then we need to study the problem and develop alternative solutions, analyze the alternative solutions to figure out which one would be the best under different conditions, and then finally make a recommendation in terms of what would be the best approach to solving the problem. So in that situation, we have two possibilities. You can either observe the system as it is operating in real time and try to figure out what would be the best solution for the problem that we are facing, or you could analyze a model. Okay. Obviously, when you analyze the system, the benefit is that you're actually looking at the actual system as it is operating, so you're getting an unfiltered analysis or unfiltered look at the system. But the disadvantage is that now you cannot interrupt the operations of the system, so to that extent you're limited in trying different alternative solutions approaches, and also it'll probably be disruptive when you try different solutions. It's time consuming, and because of all of those drawbacks, okay, it is preferable to develop a model and you analyze the model under different conditions, environmental conditions, business conditions, and then develop an appropriate solution that would be best under different conditions. Now, when you're talking about analyzing the model, then we can build a model, okay, and that model could be a physical model or it could be a logical model. A physical model is one where you actually build a prototype. So if it is an engine that you want to try a manufacturing situation, then you like, for example, in aircraft manufacturing, you'll have a wind tunnel built, and then you build a prototype and then subject it to the wind tunnel and collect data and then figure out what would be the best design. And you could do the same for process engineering, where you can set up a production process in miniature and then bring in different inputs and then see how the production process functions. So that would be a physical model. And once again, physical models are time consuming, more expensive to develop, and also may be limiting in terms of the number of scenarios that we can consider. So now you look at a logical model. So logical model, of course, is an abstraction of the actual system. So to that extent, the model may or may not truly reflect the actual system. So to the extent we are able to accurately or very closely model, the logical model resembles the actual system, the solutions that we develop will be more useful and more um, accurate in terms of predicting what will happen when we actually apply those recommended solutions. So logical model is what? It's a bunch of mathematical equations with which you try to represent the actual system, and you have two different possibilities again. So you have an analytical model. Say for example, if you have a production system where you want to come up with a reorder point solution. So you want to make sure that you reorder a part that's needed for production in such a way that you don't run out and bring the production system down because of lack of parts. At the same time, you don't want to have a lot of inventory of that part, which means that a good portion of the working capital is tied down in inventory. So you want to come up with an optimal level. So one possible analytical model is to come up with a probability of demand and how much will be used in different days of the week, and then what will happen if you have a certain level of inventory, and what is the probability of the inventory running out and things like that. So you can make calculations of this type, and then we can come up with an optimal solution. Or you can set up a simulation model where instead of coming up with strict mathematical equations, you incorporate within those equations. You still have those equations on the model, but where you have input variables, say for example, you want an input variable which is like the demand for a part in the production line. So now you're assuming in the analytical case a particular equation that will determine the demand for the part on a given day. Now in simulation, you take that equation, and suppose if that equation has some uncertain input variables, okay, for example, it has a mean of 10 parts an hour with a standard deviation of say 0.2 or something like that. Now you take that equation, and instead of coding it as a static mean plus standard deviation, so you incorporate a random element to it. So you assume a certain probability distribution with that mean and that standard deviation or other parameters, and then generate a random value from that analytical construct. So, and then you can try this iteration by replicating it any number of times, 1,000 times, 10,000 times. So that will give you a whole lot of results, and then you can analyze. So that would be a kind of a simulation model instead of an analytical model where the equations are static, whereas in simulation model the equations are more dynamic. That's our course here. So simulation modeling is what we're going to be discussing in this course. Now let's take that simulation model and break it down a little bit more. So we have two kinds of simulation model that we can think of, or at least in this course we can visualize simulation modeling in these two broad categories. So one is called Monte Carlo simulation from French Riviera, and you have event process or digital event or digital simulation, process simulation, event simulation. So Monte Carlo comes from the fact that it is a random things like in a casino. So well, but we're not going to be getting into any casinos here. All right, so let's look at the contrast between these two broad categories of simulation modeling. So one is Monte Carlo is static, not in the sense that analytical approach from the previous slide, but I'll explain a little bit more about this in just a second. This is more dynamic. So which really means time here is considered as discrete, like a bucket. So you specify, okay, I'm going to look at one day. and then you see simulate for that one day and replicate it 10,000 times, and then you analyze the results. Okay, so you don't look at time as a continuous flow. You define what time frame you're looking at, okay, a priori. So it could be a day, it could be an hour, it could be a month, it could be a year. So you define a particular time bucket, and then you simulate what will happen within the constraints of that time bucket. Whereas in event or simulation or process simulation, time is continuous. Like, you observe the system over time and then see what changes take place in the system. Okay, let me give an example. Suppose you take a customer service line, okay, call center. So you have calls coming in, and then you have operators, customer support people answering the phones and helping customers. Okay, so you have only limited number of lines, unlimited number of service operators. So you're going to have a queue or waiting line. Okay, so now you look at each call coming in and how long do they wait in line until they get to the head of the queue, and then they get served. Okay, and that service takes a bit of time, and then they leave, right? So you observe when they arrive and how long they stay in the line, and how long does the service service takes place. Okay, so observe all that, and then analyze that and prepare a report. And then you may simulate this for 1 hour or 2 days or 1 month. Okay, so but you observe the time as it flows in a continuous fashion. So that's dynamic or discrete event simulation, or simply event simulation or process simulation. So what happens, the outcome during a specified time span, as opposed to changes that take place in the states of the system over time during the time. Okay. So now example here, say you have a mobile hot dog stand. Now you want to, when you start the hot stand day, which could be the lunch time, say between 11 a.m. and 2 p.m., for example. So now you want to make sure that your stand is fully stocked, you don't run out of hot dogs, or you don't want to stock too much that you end up not selling, and then the expiry date, it becomes bad and you have to throw them away. And then you calculate the daily sales and how much profit we make, and then you replicate that. So that would be Monte Carlo. The same mobile hot dog stand. Suppose if you look at what happens between 11 a.m. and 2 p.m., minute by minute, and see how many customers are coming in, how long is the queue, what's the average wait time, and then you see how many hot dogs you sell, and on and on and on, and you find the sales and profit. So that would be a discrete event simulation. Now for Monte Carlo simulation, we have lots of options in terms of what software platform we can use. We can even use the native Excel functions. There is a VLOOKUP function, and there is a new XLOOKUP function, and we have lots of probability functions available in Excel, and we can use all of those functions to set up a Monte Carlo simulation model. We can do that. We will see some examples of that. Or you can use one of the simulation platforms, software platforms that are available, and there are many of them, and I have just listed a few here. And we will be using At Risk by Palisades. So that's what we're going to be using for this class for Monte Carlo simulation. Now for discrete event process simulation, again, there's a whole lot of packages available. There are some modules even in R and Python. But we're not going to, what we're going to do is we're going to use Pro Model. Okay. And Arena is another very popular one. SimScript and GPSS used to be quite popular, but it seems Arena is the one that's more popular than these two. And I selected Pro model because it is object oriented. It is relatively user friendly, and that's the reason why I selected Pro model. And we'll be using Pro model for the discrete event simulation part.